Hi, it's time to take a look at this ILX Lightwave LDT-5910. It's a thermoelectric temperature controller similar to the more advanced 5910B that I fixed a few months back. I originally thought the fault was limited to a smashed power supply board, which is just like the last one I repaired, but starting calibration quickly revealed a fault in the resistance sensing. So I'll show the power supply replacement fairly briefly I think, then how I fixed the constant current regulation and resistance sensing. Next I'll calibrate the unit using GPIB commands so that it measures the thermistor accurately. Finally I'll take a quick look at a program that I wrote that obtains the calibration coefficients for a specific thermistor. That helps us crank up the accuracy. It has a destroyed transformer on the board here. I searched around, I couldn't find a replacement. Now it's easy to find a replacement for this part, by the way. This is an LP12-3800, this big transformer. You can buy those off DigiKey, but this one here is a slightly more interesting beast, and I couldn't find anything with the right configuration. With no chance of getting an off-the-shelf replacement transformer, I had to roll my own board. That way I could use separate transformers for the digital side and the op amps, provided of course I could make them fit the very limited space. You might note that I'm using Easy EDA Pro instead of my usual Altium, and this is because I'm trying to make my projects more shareable. This has led to a few slip-ups. I've fixed all that now, so when I share hopefully there won't be a problem. Let's take a look at the schematic. So the top section is exactly the same as in the broken unit, and we're reusing the transformer that was in there, the LP12-3800, and as I say, you can get that from DigiKey if you need a new one. Go to a bridge rectifier and then a couple of capacitors, so it's just an unregulated supply, exactly as it was on the original board. Then we get to the point where I've had to separate out the 5 volts and the 15 volts. So the next transformer down, this is a dual secondary 15 volt, and I've arranged it as a center tap. This makes it very easy for me to get my 15 volt dual rail output for my op amps. Essentially we've just got a rectifier, 2 regulators, a 7815, a 7915, which is exactly what they did on the ILX board. The 5 volt, I did try and find a 5 volt transformer that would fit, but by the time I added in all the capacitors, the rectifiers, the regulation and things like that, there just wasn't room on the board. So I compromised and I went for 2 AC/DC converters. So these are isolated converters from Meanwell. They are an IRM 0505 and they're 1 amps each. The reason we need 2 is because GPIB has a fully isolated supply of its own. And so you'll notice on here it says isolated, do not connect to ground. So you have to make sure you get your wiring the right way around when you connect up the board as well. So this is the moment of truth, finding out whether the board actually fits or not. It's just a double-sided board. That way around I think. That looks right. Yeah, looks good. Now I haven't bothered, because it was very tight for space, to bring the 2 15 volt regulators out onto this back heatsink. If I need to, I can put independent heatsinks on both of them, but I have carefully aligned the bridge rectifier so that it would use the existing hole, which means of course I do need to take off this MB805 bridge rectifier from the original. So I'll pop him in just to make sure he is properly aligned, secure this in place. So I'm just soldering it from the top from it just to give it a good location. So I have joined up the main unit using my bench power supply to check that it generally worked. The current on the 15 volt lines is really low, so I don't think I'm going to bother with a heatsink. If I do need one, then I can just attach a small piece of aluminium to it afterwards. So I'm speeding through this, of course. It's fairly straightforward assembly, small items first, higher items later, and then towards the end I've just got to reclaim this transformer from the old board, and I think the end result looks great. I'm really hoping these are going to be long enough. Alright, there's our board finished. Fingers crossed it works. The reason I'm struggling is that the power supply unit is upside down at the front and it's covering the GPIB header. So you have to fit the GPIB first at the back. But if you do that, it covers one of the power connectors, so you can't get to it. So it's best to take the back off completely so you can actually kind of half fit them both and wiggle them about and gain access as you need to. What a terrible design. There he is, there's our power for that one in. And put this back in place to get the main power connected. Whoa, wowzer. Now, I just need to fit that in there. Put the main board back in place, reassemble it all. Oh. So I reckon we are working, so I'm pretty happy with that. Okay, so something quite interesting has just happened. It was working, except it was giving me a wrong reading. So I set out to calibrate it, and I've just been testing the GPIB, and that all seems fine. And it was reading a temperature, just not a very accurate temperature, and I would warm up the thermistor and the temperature would rise. So everything seemed to be working absolutely fine until a minute ago when it just stopped working. So E01, I've just looked that up, and that stands for AD overrange. Now before it was displaying that, it was displaying E02, which is the calculation of temperature failed. So something has definitely gone wrong there. My suspicions relate to, I suppose, constant current supply maybe. Well, we can have a look at the constant current supply, I suppose. I thought it'd be a good idea just to have a quick understanding of the principles at work here. So we've got a thermistor connected to the back of our unit, and we want to measure its resistance. And the reason we want to do that is because the resistance is proportionate to the temperature. Unfortunately, it is not a linear relationship, but to measure our resistance, we can use Ohm's law. The easiest way is that we output a constant current and we pass that through our resistor to ground. That simple, really. Now, this point here, where the constant current goes into the resistor, has a voltage, and the voltage is of course directly proportionate to whatever that resistance is, because the current is constant. So all we've got to do is measure that voltage, and then we can do the calculation resistance equals voltage divided by current. We know current because it's constant, and that's our lot. So all we have really is a constant current source going through a resistor. We then branch off with a high impedance input to an amplifier. High impedance because we don't want any current to go through there. That gets passed to an analog to digital converter, and then in our microprocessor we do something called the Steinhart-hart equation. Steinhart-hart is a way to approximate these curves, but what we want to do is we want to solve an equation to enable us to pick a resistance and turn that into a temperature. Having done that, we can then of course just display and process the temperature as we need to. So in terms of what could have gone wrong, well, an obvious thing that could have gone wrong is this constant current source. If we're outputting the wrong current, then the voltage is going to be wrong. And if we think about the errors we got error 2, which basically means I've measured the voltage, I've passed it through the amplifier, and I can't turn it into a sensible value. It doesn't make any sense. I can't solve the temperature given the resistance that I'm measuring. That then turned into error 1, which basically says the ADC is over range. So that would indicate three in fact possible places. 1, the constant current isn't what it's supposed to be. 2, there's actually a break or short circuit around this thermistor, so we don't have the resistance we're expecting. And 3, this amplifier is doing something stupid with the actual voltage. Now all this stuff's connected together, so of course it could be, something a little bit more subtle than that, but certainly measuring the constant current is going to be my first step. I've connected my multimeter in series with the thermistor, and I should read 100 microamps, and I'm reading nearly 500, so that's way out. We're getting an E02 this time, which is I can't calculate. Well, I'm not surprised. We're a very long way out in terms of our current. Let's switch our current to 10. That's 10, and it's gone to 533. So that is disaster, really, I think. So clearly our current source has failed. I think we can pretty much guarantee that our problem relates to the current sense and the current limiting. Here's our back panel with the GPIB attached, and now we can kind of see all of our connections. Just checking everything is connected correctly here. Yes, it seems to be. That seems fine. I'm feeling the temperature of the different. We've got an OPO7 here, a transistor here, and an LF356 just here, and then another OPO7 just there. So lots of questions. Which is our op amp relating to current control? So now we can begin to just trace through and see if we can figure out what's going on. So I thought it might be a nice idea just to stop looking at me trying to figure out where the circuit goes and just discuss it on a still capture. So my pointer is pointing at where the thermistor is connected, and one half of this thermistor goes directly from the input or output, as you might think about it, to this resistor just here. So just like that. The other side goes off to ground. So essentially we've got this resistor, then the thermistor going to ground. Where does this side go? Well, it goes just over here, just into this JFET. Then we can easily trace through. The gate of the JFET is joined to this 1 meg resistor, which in turn is joined to pin 6 of this op amp. This op amp is in turn connected to these 2 resistors, and the range switch. And the other input of the op amp is connected to this piece of circuitry here. So let me just write a number on here, 5 volts. So this is outputting a reference. These are our current control resistors down here. And this is controlling our current in a feedback loop, which I haven't drawn on this diagram, through this JFET up here, through this resistor and out. Now on this pin here, we can see we're also going off to this op amp, and this is essentially monitoring the voltage at this point here. So it's monitoring the voltage. So one side of your thermistor is connected to ground and the other side is connected to this op amp to find out what voltage is being formed on the thermistor. And that of course will vary as the resistance of the thermistor varies. So that's our circuit. So I put together this quick schematic just by kind of looking through the PCB to see what went where. Here, this is not a full reverse engineering of the current source. The idea is that we've got this voltage here, which is about 15 volts. It flows through one of the range resistors, whichever one we've chosen, and goes through the JFET and also goes through that resistor that we noted on the board, and then finally through the thermistor to ground. So if we change the voltage on the gate of the JFET, then we can think of it as its resistance changing, and the current flowing through this series chain here will actually alter. Since this route is in series and all of the branches of it, so we've got just this one meg branch here, and we've got this branch to the LF356, since those are all high impedance, then our current through the range resistor, our current through the JFET, through R4 and the thermistor will all be identical. That is of course if all the parts are working. So the OP07 controls the voltage across the selected range resistor by ensuring there's always a 1 volt drop across that resistor, and we can see that with that 1 volt reference just there. We always have to drop 1 volt if the inputs to the OP07 are going to be the same. If the thermistor value falls because the temperature gets hotter, well, that means that more current will flow through this series of resistors. More current flowing through it means more voltage drop across the range resistor, and therefore the op amp output will reduce, pulling the gate downwards. JFET 1 resistance essentially increases and the current starts to fall back again, and it will continue to do that until the voltage across these resistors gets back to 1 volt again, and then we reach a new point of stability. So that regulates our current. Now the LF356 over here is just a buffer. It's just going to buffer the voltage that's on the end of the thermistor, and since our current is constant, then this is going to be proportional to the resistance. So in the running simulation, we can see that I've got a 15k thermistor, but I've got 100 microamps flowing through it, just as we would expect. So it is regulating as we would expect it to regulate. We've got the right amount of current, and if we look up, we've got 15k here and we've got 1.503 volts coming out of the op amp. So we've got a direct correlation between the output of the op amp and the actual thermistor. Let's change the thermistor down to 10k, and there we go. We can see the voltage has reduced to 1, but the current is exactly the same, hasn't changed. It's being regulated. What happens if I change then across to the 10 milliamp range? Well, the current changes to 10 milliamps and the voltage going out divides by 10. Being able to change that range gives us precision across different temperature ranges. Let's just probe that carefully. So that's on 4, that's on 7. There's my 30 volts power supply. Pin 2, so that's one input, 29.02. 9.017, so that's well within the input offset expected. And what's the output? Pin 6. So it's outputting 5.9 volts, and then that obviously is going through a loop. So gate is 3. There's my 5.9 volts on the gate. Then we're sourcing 8.2 volts to the start of that resistor that we were looking at, and 7.165. 8.2. 7.655. So that's dropping 0.545 volts, and so it's 5.6k, didn't I? So I'm going to just check how much current is actually flowing through that little resistor that we talked about earlier, the one that's in series. So this is a low enough value resistor that I can just measure directly across it. 0.5477. Interesting. 0.5477 divided by 5,600 times 1 million is 97.8 microamps. 97.8 microamps. That's what it should be. Well, you know, give or take a few percent here and there. Oh, seriously? So I'm actually just going to measure this microamp again. There we go. We're connected to the resistor. 489 microamps. So I've connected up my 6.5 digit Keithley, and it's measuring 505 microamps. Well, that feels like an impossibility because I've got two resistors in series with different current flowing through them. So somewhere, some current is going where it's not supposed to. What we've just discovered is that through this resistor here, we've got our expected 100 microamps. But when it comes to here, we've got 500 microamps, or thereabouts. So we've actually got more current leaving this junction than is going into it. So we must therefore, there's only one place that extra current can be coming from, and it's got to be down that wire there from the LF356. So I'm going to change that op amp and see if that fixes our problem. Just turn that off at the mains, that's the easiest way there, and conveniently this is in a socket. Okay, so that's the LF356, 36 volt, 5 megahertz, JFET. So I do have a TL071, which is the recommended replacement. And that is a lot more convenient just to be able to use the right thing. It is the Texas Instruments drop-in replacement that they recommend. So there we go, one TL071 in place. Powering up. And Eureka, 27.1 centigrade. It's probably a little bit high, maybe a degree high, something like that. But now we've got that part in, we can actually recalibrate this to take account of any, for example, input offsets on that part and get going. So yeah, bit of a pain tracing through. Let's put it into the 100 milliamp range, which should give us a better, and measure that, 940 millivolts. So that again is about right for 100 microamps going through those resistors. So that seems to have solved our problem. Happy days. So clearly we had a nasty current leakage going on there. Right, let's get this reassembled and then I can actually recalibrate. So I'm ready to calibrate this. There are two types of calibration. The first is for the unit itself, and that's so it can read resistances very accurately, because if it can't do that, then it's never going to be able to work out the temperature. And as we saw in the circuit diagram, there are relatively low tolerance resistors involved, 5% resistor for example on the output, and only 1% resistors on the current control circuit. So the op amps involved as well have input voltage offsets. We want to calibrate all of that out if we can. To do that, we use two known resistors. We want to use pretty much the full range, the 4 digits that we have available. We need something between 9 and 9.999, or 90k and 99.9k. So something in those regions. It doesn't actually matter what they are, because we're going to measure them accurately first. Thermally stable metal film resistors. So what I'm going to do is I'm going to measure these resistors. I'm just going to write those down. This is a 4-wire resistance measurement on a 6.5 digit calibrated meter. And we have 95.266k. So I've got 4 digit significance on my meter. So I need to measure these to 5 digits. And this one is 9.5218. So I've got those measured accurately. So now what I need to do is join one up. So I've chosen 100 microamps. I'm therefore going to want to connect up the 10k resistor, or roughly 10k resistor. Okay, and it thinks it's found a temperature. Now I've just been handling that, so I'm just going to let that cool down for a second, and we shall move across to the screen. And here's our alias LDT-5910, and yeah, happy with that. So let's go to the interactive I/O, and there we go. It has connected to my instrument. So we've got our resistor connected, we've got our GPIB connected. And now it's actually time to do something. We want to display what the device thinks that resistance is, because the way we're going to do this is that we're going to look at the resistance that it thinks it is, and we're going to work out by what percentage or what proportion that is incorrect. We're then going to pull up a parameter, so there's a coefficient in there which is used in the maths to change the voltage reading that it's doing on the op amp into a resistance reading. We need to trim that to get it right. We need to do that for both current ranges. So currently we're on the 100 microamp range, and we've got a 9.5218k resistor attached. So we want it to read 9.522. I have got a manual with all the commands in. So we're doing the Cal R10 value. So I need G6 and P6. So G6 is going to get the calibration value for the resistor 10 range. Before we do that, we need to find out what we think the resistance is. So what we're going to do is we're going to turn this, instead of displaying the temperature, we can do D5, which is resistance display mode. So that's what we're going to do. So we go over here, we type in D5, and we do send and receive, and it thinks the resistor is a 9.492k resistor. And we can see that on the screen and on the interactive I/O. So as I get my calculator out, I work out what percentage it's off. So 9.5218 divided by 9.492, and there we go, it is 1.003139, etc, etc. So I'm just going to leave that in my calculator. So we're 0.3% off on our reading, which isn't really bad, is it, to be perfectly honest, but we can get better. Now I need to read that number we were just talking about, so I need to do G6, send receive, and that returns 11102 as the number that it's internally multiplying everything by in order to get that 9.492. So I need to increase that, so I take my calculator value that I've just worked out and times 11102. So that tells me that I need to input, sorry, there's a lot of reflection on my calculator, 11136.9, so 11137. So I do numeric value n 11137. I need to put that value into position 6 because I've got it from position 6. So let's do a send and receive now. And if we look on the screen, we can see that we have gone to 9.522, well, somewhere between 9.510 and 9.522, and we're aiming at 9.522. So pretty happy with that. That's just the noise. The reason it's moving so much is because where we are in the ADC, the ADC resolution. So we either read 10 or we read 22. This is only 1 bit difference in the ADC. So let's repeat that now then with the 100K. So I'm going to go for 93.93 because that seems to be roundabout in the center. So in the same way, I'm about 1%. So just like I did before, G7 this time because I need to get the right value. And there is my adjustment factor, 109 blah blah blah. So I multiply by the error, 10987. That gives me 11143. And 11143 P7. And send and receive. And now if we look on the screen, we're going 95.16, 95.38, and we're kind of in the middle of that range. 95.266 is the actual value of the resistor we've got connected, but we are picking up a bit of noise. Okay, so that's that bit done. Now we can continue, we can connect up an amp meter to the outputs, and we can do a similar calibration, essentially exactly the same method for the current limit setting on here. So essentially we set an amp, we see how close to an amp we're outputting, and then we just adjust a factor to make it work better. So we're just trimming a DAC is all we're doing for that. So it's the same principle. So having calibrated our unit, the next question is, what about the thermistor itself? I mean, thermistors all come from different manufacturers, and they're never going to have the same curve. And on the screen, I've got typical curves for various different thermistors. Now, what we need to do in our computer program that's buried in the microcontroller of the unit is that we need to read our resistance, so let's say 10K, and then translate that into a temperature, let's say 23 centigrade on this graph. That isn't very easy, is it? Because this, of course, is a curve, and in fact the curves from different manufacturers for 10K thermistor will vary. So how are we to achieve a reasonable degree of accuracy? Well, the answer is there is an equation which approximates this curve, and it's called the Steinhart-hart equation, and it has 3 coefficients that essentially take a logarithmic curve and lift it, stretch it, twist it to actually fit the curve of your specific device. So in order to do that, you've got to take lots of very precise temperature readings and then solve a lot of maths in order to work out the 3 coefficients for your device. ILX actually provide some of the coefficients for certain make. It tells you some values that you can use for the coefficients, and you'll see there's quite a lot of variety in these coefficients, even in the same manufacturer for their different types of thermistor. So how do we kind of solve this problem? Well, here are some computer programs that they provided in Basic A, which was an old IBM Basic, and what I've done is I've translated those into a modern C# program that looks like this. So this one at the moment is showing some recordings for a Dale thermistor, and what I'm going to do is I'm going to drop in the temperature readings for mine. So my thermistor is an NTC thermistor from Vishay, the NTC LG100E2, and then mine will be a 103JB because it's a 10K resistor. And if we look further down, they've very kindly provided typical resistance curves against temperature for each of their thermistors. course, if you've got a lab and a dry well or dry block calibrator and a super duper 0.01% accurate thermometer, then you could do this yourself. And it's easy to get. A couple of points, 0 and 100 centigrade, are very easy, but you're going to need at least 4 or 5 points in order to calibrate your thermistor. Manufacturer's data is definitely the way to go. So I've got this one, it's called templist.txt. I can take this, I can drop it on my computer program. It tells me what I'm importing, and then it imports it. And so here we go, -40, the resistance that it finds there, and it's worked out a curve with coefficients at the bottom. So C1, C2, C3 coefficients, and what it's done then is done what the actual unit will do and converted them back and tried to work out, if I receive that number of ohms and I apply these coefficients, how far off the true reading will I be? Well, here's 25 degrees centigrade, and the answer is I will be 0.05 degrees below the optimal reading. The more points you add in, the better it's going to be. And as we go towards the top, I got bored and didn't bother entering quite so many values. So I went, instead of 90, 95, 100, 150, 200. I just skipped a lot, and you can see the accuracy has actually suffered in that little area because I didn't give it many readings to match up to. But in other places like 45C, the accuracy is absolutely stunning. So it's a very good, simple program, and and of course you can just click add and stick in some more resistances and stuff yourself if you wanted to. I will make this program available, so I'm going to go and transfer these onto my actual unit and see how all that works. Back in the lab with my readings. So one way you can put the readings in is to actually use the front panel. So if I do select to C1, and it's supposed to be what, 1.147. So I can hold that down and I can try and dial it in. As you can see, it's very, very temperamental. Missed it. I did actually just manage to get that one, amazingly. So it's very tricky to just get those precise values, extremely dodgy. So I am going instead to use the GPIB, N1.001. This is C3, so then it's P5. I'll send and read, and then I'll do N2.311. P, and this is C2, so only P4. It's not exactly intuitive, I know. Send and receive. Oops, 2000 I've put in there. N2.311 P4. Excellent. So now my unit is displaying 28.2 as its temperature. Okay, so I've tried to put everything as close together as I can. And here's my reading on here, and here's my reading with my thermocouple. So pretty damn good. So of course I don't really know exactly how accurate that is. It looks about right, but I calibrated it using the datasheet, using typical values for the type of thermistor that I've got, rather than an actual calibration. And the reason for that is, of course, I don't own a couple of £1,000 worth of dry well or dry block calibrator, and so got to do the best we can with what we've got. We could test and see how close we are by putting it in some iced water, or of course into some boiling water, using distilled water at the right air pressure and all that sort of stuff, but I think I'm pretty happy. So if you enjoyed that, don't forget to like, subscribe, share if you can, and leave some comments. I'll see you soon. Bye for now.